What do you want? Yeah.
There was a question on the last website number 4. It was
The one with the cars?
no, it was finding error bonds and
Yeah.
it was the integration of 27 cosine x squared dx.
Oh, that one.
Yeah, I couldn't find
From what to what?
0 to 1.
Okay. So this is really by Simpsons. Am I writing big enough in the back? Okay. Simpson, right?
Oh no,
Trapezoid.
And
Okay.
8 and
8. Okay, so that's the problem. Does anyone need me to actually do the problem, the trapezoidal approximation of this? Yes? No? Okay. There's an answer. It's either yes or it's no. Does anyone want me to actually write down what T8 is?
Sure. Yes.
She does. Okay. So T8. So what we do is we take our interval from 0 to 1 and we divide it up into 8 chunks. 1, 2, 3, 4, 5, 6, 7, 8. And our x's that we're going to evaluate are the edges of each of these chunks. So this first one will be 1/8, then 2/8, which is a quarter, then 3/8, then 4/8, which is a half, then 5/8, then 6/8, which is 3/4, then 7/8, and 1. And for the midpoint, we have to use the middle of these things. Let me skip the midpoint. Let's just do the trapezoid. I'll do the midpoint if you really want. Okay? And so now what we do, the trapezoid says we erect, we look at our function, it does whatever it does here, and we put little bars here, and we connect the dots. And we find the area underneath what we get when we connect the dots. So the width of each of these things is 1/8. And the height of each of these, the area of each of this thing is this side plus this side over 2. So the height is however long this is plus however long this is over 2. So it's going to be, since they're all over 2, I might as well take a half. And now it's going to be f of 0 plus f of 1/8. But in fact, when I do this one, the f of the 1/8 plays a role, and then when I do the next one, the f of the 1/8 plays a role, so there's going to be 2 of those. And so on, whatever they are. 3/8 is next, blah, blah, blah. So in this case, it's 1/16. Oh, there's a 27 out here. Let me just pull the 27 out front. So it's 27/16 of, now f of 0 is the cosine of 0 squared. 2 times the cosine of 1/8, but it's squared, so it's really 1/64. 2 times the cosine of 3/8, well, 3 squared is 9, and 8 squared is 64. You can go all the way over to there, so I might as well keep going. Yeah, let me just keep going here. So let me not write them all down. Does anyone not understand what's next? Next one is the cosine of, I skipped a quarter. Sorry, this is a 16th. This is a quarter. So this is a 16th. And this is 9/64, etc. Plus 2 times the cosine of 7/8 squared plus the cosine of 1 squared. So then you plug all this junk into your calculator and you get the answer.
Are we allowed to calculate on the exam?
No, but on the exam, I won't ask such a nasty thing. On the exam, if you have an answer like 1/16 of 1/2 plus 7/8 plus 19/64 plus 22/7, that answer is correct, assuming that those are the right numbers. You don't need to add those things together. Unless it's something stupid like 1/2 of 4 plus 3. Well, how about 4 plus 8? I would like you to write that as 6. But, okay, that wasn't your question. So for the midpoint, which I just erased, it's exactly the same, except we only evaluate here in the middles, which I don't want to write down, and we multiply everything by 1, because we're just taking the height of the middles. If you think about these things in terms of the picture, there's sort of no way to go wrong. Okay, but your question was about the error.
Yes.
Right. So I do this, I get some number, and the second part says, what's the error? And let me just do T8. It works the same way. Okay, so there's a formula. You don't need to memorize the formula for the exam. I will give it to you if you need it. Let's see if I remember the formula. The formula is, so the error is less than k times b minus a cubed over, I think it's 12n squared. I think that's the formula. Okay. So b minus a, that's easy. This is 1 minus 0. That's 1. Just forget that. We need to find k. Here, k is the maximum for x between 0 and 1, or my a and my b, of the second derivative of x. So we need to take the second derivative and then say, where will it be its biggest? So, okay. So here, we need to take the second derivative of our function. So our function is 27 cosine x squared. So our first derivative, we have to use the chain rule, is 27 times 2x times the sine of x squared, and it's negative. And the second derivative, which is the one we want, is 54. Well, let me not reduce it yet. Just leave it out. Yeah, let me leave it as 54. And now I want to take the derivative of x sine x squared. So I use the product rule. The derivative of x is 1, so I have sine x squared. And now I take the derivative of this piece, gives me x times 2x times the cosine of x squared. There's a negative sign that I lost. Doesn't matter because I'm taking an absolute value. Now, we want to maximize this between 0 and 1. But the problem tells you, don't worry about where the cosine and the sine exactly are the biggest. Just notice that sine of x is always less than 1 in absolute value, and so is the cosine. And since this is just an estimate, it's okay to just replace the sine and the cosine by 1, because they're never bigger than 1. So this is always less than well, we have a 54. I'm going to replace that by 1 plus 2. Now, x squared is biggest when x is 1, not when x is 0, so I can replace that by 1. And I replace the cosine by 1. So the k that I want is 3 times 54, which is 162. So assuming I didn't make any arithmetic errors, I want k to be 162. And then, so now let's go back here. And so our error is less than or equal to 162 over 12 times n squared. N was 8, so that's 64. So that's some number. It's not very good. Well, it's all right. It's whatever it is. It's some number. You can plug it into your calculator and it's like 0.02 or something. Does anyone know? Does anyone care? Okay, all the same. Okay, so does that answer your question? And for the midpoint, this is a 24. So the midpoint, it's exactly the same except it's half of that. And here we have to do something different for the midpoint. Other questions? Yeah?
You go for a trig sub and arc sine.
Okay. You want a trig sub with arc sine. Okay. Let me put this here. Do you have one in mind? Okay. Do you want me to do an easy one or a hard one? Well, a hard one's going to take like an hour and a half. What do you want?
Easy one.
Okay, so I'm just going to make this up. So, do you want it definite or indefinite? Okay. So, this one may come out icky. The numbers might be nasty, but and do you want it? Okay, you want it middle hard or? Okay. Here, let's just do this one. I can make it harder if you want. Is that hard enough? Or that's fine? Okay. So say I have something like that. Yeah?
How hard are they going to be on the test? Why not just do ones about that difficult?
I don't know how hard the one on the test is anymore because I know how to do it. This one is probably okay. So let me point out how it could be a little harder. So there's two ways that it can be hard. Number one, it can be hard because you don't recognize it as a trig substitution because maybe there's a 5 here and the constants are ugly and this isn't a 4, it's a 14, and now I'm going to have a square root of 5 and a square root of 14 floating around, and it's just nasty. But conceptually, it's no harder. It's just nasty. So I don't want to drag around square root of 5s and square root of 14s. So that's one way it can be harder. Another way it can be harder is that the trigonometric integral that we wind up with can be hard. I don't know what the trigonometric integral we're going to wind up with is on this one because I just wrote it down. I don't think it's hard, but we'll see. It may be horrible, but it's doable. So this is probably about a good level of difficulty. All right, so here I look at this and I say, I hate this square root. I want it to go away. And I remember that sine squared plus cosine squared is 1, so that means that sine squared is 1 minus the cosine squared. Or maybe I wanted cosine, because you wanted arc sine. Okay. So rewrite it as cosine squared is 1 minus the sine squared. And so if this x were only some kind of sine, then what's under the square root would be a cosine squared, and I could take the square root, and it would be great. So I just want to transform this into something that looks like 1 minus something squared. Well, it's not a 1, it's a 4. But I can factor the 4 out, which is really a 2. So I can rewrite this as... So I'm going to pull the 4 out, but I'll leave it inside for now. And now I have an x squared over 4, which I can also write as x squared over 2. Alternatively, you can just let x be 2 sine squared. It's the same. So everybody okay with this so far? All right. So this is an x over 2. And so now I'm going to make the substitution. X over 2, I want that to be a sine. Or if you prefer, x is 2 sine theta. They're the same. And so that means that dx over 2 is a cosine like that. And so here, for dx is, did I make a mistake? No. 2 cosine theta d theta. And I'm running out of board space unless I want to sit on the floor, so I'll come over here. So I'm going to make that substitution. So x is 2 sine theta. So this becomes, so my dx becomes 2 cosine theta d theta. My x becomes a 2 sine theta. That's my x. And my square root becomes 1 minus sine squared. So that's just plugging in. The 4 got eaten in this 2. And in this 2. Did I lose something? X is 2 sine theta. Well, somehow no, that's my x. Right, this is x, 1 minus x squared over 2. And this is dx. Yeah?
Can you also make like x into sine theta?
If you like, sure. You'll get the same answer in the end. Doesn't matter. I mean, I'm doing it with sine because he wanted sine, but cosine will work exactly the same. I'll get a negative sign, but then when I integrate, it goes away, and it's all the same. Yeah?
Could you explain where the 4 went?
Okay. I don't know where the 4 went, actually. The 4 went on the floor. There's another 2 here. Okay. Thank you for being persistent about explaining where the 4 went. It went away because I found it annoying. Okay, the square root of 4 is 2. So I can pull that out, and this 2 becomes a 4. So just to simplify, take the square root, it's a 2. These 2's cancel, and so I get a 2. And now I have cosine theta. And here I have a sine theta. And here I have, so this one is nasty. So now I have 1 minus sine squared, which is the square root of a cosine squared, which gives me a single cosine. So this one's nasty, or it's not, depending. This is an integral I hate. So this is 1/2 the integral, the cosines cancel, d theta over sine theta, which is 1/2 the integral of the the cosecant theta d theta. So this is not my favorite integral. And I forget how to do this one. It's the log of the cosecant plus the cotangent, I think. It's negative log of cosecant plus cotangent. So we can work backwards. So the reason I hate this integral is it's a completely non-obvious substitution that makes it work. And I've forgotten what it is. So you can probably suspect that if you see the integral of the cosecant, since I hate this integral, anyway, okay, that was a hint. Okay, so this is negative 1/2 the log of the cosecant plus the cotangent of theta plus constant. Now, who asked about the cosine? Somebody. You did. I think if I had done the cosine, I would get the secant plus the tangent. And I would get the integral of the secant. They'll be the same when we substitute back what theta is in terms of x. But I think if I had done the cosine substitutions, it would be a secant, and those cosecants and stuff would be secants. I'm not 100% sure, and it wouldn't be negative, it'd be positive. I'm not 100% sure, but I'm pretty sure. Okay. So this is almost done, but not really, because the integral was expressed in terms of x, and there were no thetas around. So we need to turn it back to in terms of x. If this had been a definite integral, we would be done, because when we did this transformation, we could have plugged in terms of theta and just evaluated and been happy. But it's not, so we have to ask if x equals, well, how about x over 2? So if x over 2 is sine theta, then what's cosecant theta and cotangent theta? So we have to answer that question. So to do this, usually I draw a triangle, because both of these things are really just ways of writing the Pythagorean theorem. So we just draw a right triangle here, where x over 2 is the sine of theta. So that would mean that the opposite over the hypotenuse, this triangle has x over 2 equal to the sine of theta. And then we can use the Pythagorean theorem to figure out what the other side is. So this squared plus this squared equals this squared. So that means x squared plus 4, x squared plus a thing equals 4. So the thing is 4 minus x squared. Well, we have to take the square root. It often happens, it doesn't always happen, but it often happens that your thing that you substituted for turns out to be related to the other side. I don't want to say it always happens, but it does often happen that you'll get the other side to be similar to the thing that you wanted to make go away in the first place. Okay, so now we can read off from this what the cosecant is. The cosecant is 1 over the cosine, which means it's this over this. And the cotangent is this over this. Really? Sine over cosine, cosine over sine, right? Yeah. So it's that. Right? I believe so. Cosecant's 1 over sine, and I wrote cosine. Thank you. Cosecant is 2 over x. That looks better. And the cotangent is 4 minus x squared over x. That's better. So that means that this becomes negative 1/2 the log of 2 over x plus square root 4 minus x squared x. And had you done the substitution in terms of the cosine, you would just permute the things in the triangle and you would get the same answer. Okay? Is this hard enough for you but not too hard? So they don't. The thing that gets hard about these things, once you see the substitution to make, is that sometimes these integrals come out to be horrible. They come out to be something like, I don't know, sine to the 8th cosine to the 4th, which means you have to do this half angle thing a bunch of times, and it's just nasty. Okay, other things you want me to go over?
So the test isn't going to say use trig substitution?
No.
You just have to figure out
So,
what...
so one of the sample tests, I don't know if you've looked at the sample test, one of them, some of them said do this, do that, do the other thing. So I mean, I can tell you, the test has 9 questions. I think 6 or 7 of them are integrals, but I don't tell you how to do any of them. It's just, here's 6 or 7 integrals, do them. I don't remember exactly whether it's 6 or 7. There are definitely 9 questions, yeah.
So in the test, can we use the arcsine, theta equals arcsine x over 2?
Yeah, it's the same thing.
Okay, so we don't have to use this number.
What?
I mean, oh, I understand.
You don't have to use the triangle thing?
Yeah.
Well, you have to know what the cosecant of arcsine is, and you have to know what the cotangent of arcsine is. And the only way I know how to know what, unless you just know them all, the easiest way to understand what the cotangent of the arcsine is by drawing a picture. But if you hate pictures, there are plenty of people that can do this without pictures. So I don't care what method you use, as long as A, it's not cheating, and B, your method makes sense and it doesn't just come to you from, extrasensory perception. Because it's very hard to tell extrasensory perception from cheating. On all of the questions, you do have to, none of the questions say, show your work, but I want you to justify your answer. That means show your work. It means, so I hate the phrase show your work, because sometimes you can look at something and say, oh, I know the answer to that. It's 3x squared plus 2. Pah! You just write it down. But there's something that went on inside, and how do I know that 3x squared plus 2 is the right answer? So really, I want you to justify your answer so that somebody who doesn't know it knows where it came from. Okay, that's what people mean when they say show your work. My son used to fail math tests because they would say show your work, and he said, I didn't write anything down, I just did it all in my head. And they used to give him 0 because they told him he cheated. Anyway, next topic. Or you all know it. We're done. Okay, see ya. You had a question, right?
One of the tests you wrote show some work.
Okay, so of the tests that are listed, I only wrote the Math 126 test. All the other ones were written by other people that I just grabbed. So the show some work was written by Professor Jones. He meant justify your answer. Some of them do say show your work. Or there's one of them that says, I don't care if you show any work, just write the right answer, that's good. There's one that's like matching. And he said, I don't care, just give me, this integral is A, this integral is number D, this number, whatever. I don't use the phrase show your work. But, so what? Yeah?
I have a question. How do I determine the integral converges or
The integral of convergence?
no, the integral.
Oh, whether an integral converges. Good, because what you were asking, we're not starting for 2 weeks. So. Whether an integral converges or diverges. So, this is related to, but may not be obviously as. So if we have so the most obvious one is if we have something like, well, let me do one that's internal. 0 to 5 of 1 over x squared how about that? We'll just make it easy. I have something like that. Now this may be phrased as determine whether this integral converges or diverges, or it may be phrased as evaluate the integral, and if it diverges, tell me it diverges. So if you look at this, it's not obviously an improper integral. But it is obviously an improper integral if you look at it, because 1 over 0 is not defined. So we have a problem here. And we have to say, does it make sense even though there's this trouble at 0? And so what we really want to say is this is the limit as L goes to 0 from above of the integral from L to 5. That. Now this integral is easy. The integral of x to the negative 2 is negative 1/3, wrong way, negative 1 over x. Right? Assuming I can do my integral right, which I can't always. And so now we want to know, does this limit make sense? So when I plug in 5, this is good. So I get negative 1/5. But when I plug in L, 1 over L. And now if I take the limit as x goes to 0, this blows up. So this blows up. So this diverges. If I change the problem, we do almost exactly the same problem. Not L. That problem, then it will converge. We do it the same way, but we get a different answer. So this will be the limit as L goes to 0 from above of that integral. So when I do that integral, I get, so this is x to the negative 1/2. So when I integrate it, I get x to the 1/2. So I get 2x to the 1/2, which I'm evaluating from L to 5. So now this is, I'm still writing with the limit. You don't have to write all of these steps in between, just some of them, or at least one of them. So this is 2 square root 5 minus 2 square root L, and as L goes to 0, this goes to 0. So this guy converges to 2 square root 5. This is saying, in this picture, this area is infinite. But for this picture, which looks almost the same, it hugs this much tighter. And this area is 2 square root 5. Okay? It's also possible that, let me just do one more. Again, I'm choosing easier ones on purpose, but really they're all the same. It's also possible that maybe, this was the integral from negative 1 to 5 of dx over x squared. And if you had this one, if you just did the integral and plugged in, you'd get a number. But this diverges, because this is the same as the integral from negative 1 to 0. And this diverges because we just did it. So does this. But if you just were not very observant and you just did this integral and plugged in 5 and plugged in minus 1, you would get a number. You would just get a nonsense answer. That, I forgot. Somebody over here asked. Does that answer your question? It's also possible that the things go to infinity. It's the same. You just take the limit to infinity. Yeah?
How do you tell odd functions from even functions?
How do we tell odd functions or even functions? This is a Math 123 question. You're in the wrong class. Sorry, go away. Oh, sorry. So, f of x is even. So this is the definition. If f of, let me use a instead of x, is the same as f of minus a. So if you just plug in a negative thing, and the negatives all go away, then it's even. It's odd if f of a equals minus f of minus a. So if you plug in the negative sign and you can factor it out and it just changes the sign, then it's odd. So the reason I'm sure you're asking is because if I have a function which is, say, even, well, or odd, let's say I have an odd function like, I don't know, sine of x over at 0, so I can plus, wait a minute, that's fine, plus 1. So this function is is odd, because when I plug in negative x, this stays the same, this stays the same, this stays the same, this changes sign. So this is odd. So an integral like negative 5 to 5 of sine x over x squared plus 5x to the 22 plus 1, this is 0 automatically. Because the oddness means that the negative part cancels out the positive part. So we don't have to do any work, we can just look and say, oh, it's odd, yay, happy times. And if it's even, we can just do it by splitting it at 0 and doubling the answer. Is that why you asked?
Yeah.
Okay. So I think there's on 1 or 2 of the practice tests, there's some integral which is just completely horrible. But it happens to be an even function, no, an odd function. So the answer is 0. You don't have to do any work. It looks something like this in fact. It might even be on the Math 126. Other questions? Yeah. Okay. So the comparison test is related to this kind of thing. Well, or this kind of thing. It's related to these improper integrals. Suppose, okay, so I have, let's take this one, just because it's on the board. So we know this thing diverges. If I have something that's bigger than this, so if I have something like the integral from 0 to 5 of dx over x squared plus, I want it bigger, minus 4. In fact, that's good enough. So if I look at this one, I can say, well, you know what, this looks a whole lot like that. And I know that diverges. But what does a whole lot mean? Well, for any x between 0 and 5, this number, oh shoot. Okay, now we're good. No, we're still screwed. Sorry. So I always blow it on these. Okay, so this one doesn't quite work because it's got a problem at 2. Okay, so this is a bad example, and I'm having trouble making it work. Shoot. Okay, I'm going to change this from a 5 to a 1. Still true. I mean, this is now a 1. This is now a 1. This is now a 1. It still diverges. It's still true. And now we're good. And maybe there's a 10 here. I don't care. Doesn't matter. So this thing is bigger than that thing. One, we know that this is bigger than that, isn't it? Except in absolute value. Right? So for all the guys in there, that's bigger. But this diverges. And remember, diverges means gets really, really big. And so this has to diverge because this is bigger than that. So the comparison test says, if you have an integral where the integrand, the thing under the integral sign, is bigger than the integrand of a divergent integral, then it diverges. If the smaller thing is going to infinity, the bigger thing has to go to infinity. And then there's the other side, which says that, let me erase this jump now. The other side says that, similarly, if we've got a thing which is smaller in absolute value, so the other side, so let me just write the comparison. So if f of x is bigger than g of x on my interval, and really we can do it with absolute values. It's okay. And the integral diverges, then so does f. If the little one, the little one diverges, the big one does too. And then there's the other half, if, and b could be, any of these could be infinity. And if the integral of f converges, so it's some number, so does g. So if something is going to infinity and you're sitting on top of it, you go to infinity too. If something stays at a given height and you're underneath it, you don't get any taller. So if I plant a beanstalk in this room and I let it grow, it doesn't get any higher than the ceiling unless it breaks the ceiling. The ceiling's sitting there. So the ceiling converges. It's just sitting there the whole time. I plant a beanstalk which could grow infinitely tall in this room. No, it can't. It can only get that high. That's what this is. Yeah?
I did choose a function to compare it to.
You know some stuff? So, I mean, that's the hard part of this. You need to have a little arsenal of functions in your hand that you know converge. So, you already know, or you can know, well, if you did your homework, you know, that these guys, you know all about them, whether they're going to 0 or to infinity. There was a homework problem that said, but you can just check. These guys, if we're going to 0, so then they converge if the power is less than 1. So if there's a 0 here, then this converges for p less than 1. And these guys, same guys, and they're going to infinity, they converge for p greater than 1, and they diverge otherwise. So if the power is big and you're going to infinity, the power on the bottom is big, then it converges. If the power is small and you're going to 0, then it converges. Otherwise, no. So the good things to compare to often are 1 over x to some power. Because you know about these. And they're easy. And they're ones that you should remember. There are other ones that maybe you know. Like there's, I mean, I could have also done this one by trig substitution and taken the limit and blah, blah, blah. So I can find this one exactly because it's an integral that I know. It's an arc sine. Right? It's 10 times the arc sine of x over 2 twice. Sorry, you've got to factor the 4 out, x squared minus 1. Oops, arcsecant. Sorry. Anyway, I know this one. I could do this one. But it doesn't matter. I don't have to. We okay with that? You asked about comparison. Are you satisfied? Okay. Anyone else? More comparison-related things? Okay. Other stuff? Yeah.
Just to clarify what you said before about the even and odd functions, if
it's not functioning, it's not going to the same number, like, if A isn't the same as B, is that
And it's
negative?
no use to you.
Then you still can't do it?
Well, what does can't do it mean? So you can't, so if it's an odd function, the fact about odd functions is that, I guess I can write here. So the thing about odd functions is that they tell you whatever happens over here, but underneath. And so if I'm going to something balanced, then this cancels that out. But if I've got some more stuff over here, well, then I can only cancel out this much, and I still got to know about that. So odd functions and even functions are mostly only useful when your thing is symmetric about 0. I mean, they're still even and odd, but it doesn't tell you a whole lot if it's not symmetric about the point that you're, it's the middle of your integration. Okay? Other stuff? Everybody's ready? So let's see, what didn't we talk about? Let me just remind you what we didn't talk about. We didn't talk about substitution. I assume you're all good with that. We didn't talk about integration by part. Oh, you have a question?
Yeah. You go over Simpson's rules.
Okay. I did that first. Oh, no, I didn't. I did midpoint trapezoid. Okay. So you want me to go over it with an example? Do you want me to go over Simpson's rule, just remind you how it works, and then do an example? Or do you have a specific example in mind? You can make one up, doesn't matter. Do you have one or no? Okay, so let me make one up. Let's do one where we know the answer. So let's do the integral from 0 to 1 of 1 over 1 plus x squared. This one we know the answer. The answer is pi over 4. Right? Because this integral is one you know. This is the arctan 1 minus the arctan 0. The arctan of 1 is pi over 4. Pi over 4. So this is pi over 4. In fact, let's make it even easier. We know it's pi. So when we do it, we should get an answer near 3. 3.1, blah, blah, blah. Okay. What n do you want? It has to be even, because what we do in Simpson's rule, let me remind you of the picture of Simpson's rule. So 1 over 1 plus x squared looks like this. We're going from 0, let's put 1 here, to 1. And what we do with Simpson's rule, we pick a number of intervals to chop it into 1, 2, 4, 3, whatever. So let me just draw the picture with 2. So if I'm doing it with 2, I break it into 2 pieces. And on these 2 pieces, I evaluate the 2 ends and the middle on each piece. So if I'm doing n equals 2, I'm going to use, this is n equals 4. And I have 0, 1, 2, 3, 4 points. So I have a total of 5 points. For Simpson's rule, n always has to be even because we use the 2 sides in the middle. And if n is not even, we don't have 2 sides in the middle. If it's odd, there's something funny here. Okay? So what n would you like? 2, 4, 6? Give me an n. 2? You want the easiest possible one. Okay. So n equals 2. So n equals 2 is a little bit atypical because we're just using one interval. So n equals 2, we have 3 points we need to find. So for n equals 2, we're going from 0 to 1. We want to find 3 points equally spaced, 0 to 1. So there's 0, 1/2, and 1. There we go. That's it. So since n is 2, Simpson's rule tells us that we take 1/3, which is our averaging constant. So Simpson's rule always has a 1/3. And then the width of this thing, which is a 1/2. And then we evaluate our function at each of the points. I'm going to wrap around here. But we do kind of a funny averaging that the middle counts more. If we had been doing instead n equals 4, then this one would be a 2, and then we would have a 4, and then a 1. So it goes 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 1. So since we're only doing 2, there's nothing with a coefficient of 2. So in this case, we get a 6th here. F of x 0, that means we plug 0 into our function. That's 4 over 1 plus 0. And then we have 4 times f of x1. x1 is a 1/2. So that's 4 over 1 plus 1/2 squared is a 1/4. And then 1 times 4 over 1 plus 1 squared. So this is arithmetic that I can actually do. This is about the limit of my arithmetic abilities, but okay. So this is 1/6, 4, plus 16. So 1 plus a 1/4 is 5/4. I flip it, I get 4/5. And 4 over 1, that's 2. 16 times 4/5 is 64 over 5. So that's 1/6 times 6 plus 64 over 5. So that's 1 plus 64 over 30, which is around 3 and change. So it's about right. I mean, it's some number, right? This is 94 over 30, which is 3 and 4/30, which is around pi. So I know it's about right. Had I done n equals 4, I would have had 3 more terms contributing to the mix, and I would have gotten a better answer.
What's the coefficient again?
The pattern is we count the middles 4 times the edges, but the interior edges, since they're the edge from the right and the edge from the left, count twice. So it's 1, 4, 2, 4, 2, 4, 2, 4, 1. Now this is really, oh, it doesn't matter. Yeah.
Question. If the first specific value has no sense, so how to use this?
Has no sense. You're talking about paper homework in your problem 2. It has sense. You just have to use integration by parts to get it to have sense. So if you try and do, you're talking about paper homework problem where you have to do Simpson's rule. I mean, I told you exactly what to do, but you had to read what I wrote, which makes it hard. 0 to 1, log, cosine, something like that. So you try and plug in, you get infinity. It's no good. You can't use Simpson's rule directly. So instead, you integrate by parts. Gives you something where you can, as long as you take limits. So really, remember, this is an improper integral. So this is the limit as L goes to 0 from above But even this limit is no good until you integrate by parts to make it better. When you integrate by parts, then the limit makes sense, and everything's good. Which is what I tried to say in the words when I wrote the problem, but now you can do the problem. Maybe. Somebody over here has a question? No? Okay. So let me remind you of the topics the exam covers, and then you can say, one of those. So substitution, of course, integration by parts, then various techniques of integration, which include powers of trig functions, so, sine to the m, cosine to the n, trig substitutions, integration by partial fractions, improper integrals, which we just talked about, and area between curves. It's short, it's easy exam. You know all of those things. So I don't need to do any more. Is that true? Yeah.
When you think about the sine and
Sure. I don't know where I am anymore. I started over there. No. Okay, so this is really just observations about appropriate powers of functions of sines and cosines. So for example, and it doesn't matter if the powers are negative, it's still the same. Sine cubed x over cosine squared x dx. Same. So if we use the fact that sine squared plus cosine squared is 1, that means we can turn even numbers of cosines into sines and even powers of sines into cosines. And so using this fact, we can turn this into something where we have an extra sign laying around and everything else is in terms of cosines. And then this gives us an easy substitution to make. See, if this power was 1, we're done. U equals cosine. This is 1 over u du, negative. 1 over u squared du, negative. Easy. But it's not a 1, it's a 3. So we want it to be a 1. So we'll use this fact. Let me just do this example and then I'll write the rule. So we can use this fact to turn all but one of these signs into cosines. So this is, peel away 2 of those signs, and now I'm going to turn this guy into cosine. And now, it's an easy substitution. I let u be the cosine, so du is minus the sine, which is sitting right there. Oops. How did my dx get to the bottom there? Doesn't make any sense. Sorry. My du is sitting right there. So this becomes, what does it become? 1 minus u squared over u squared and this is a negative du. And that integral is easy. Split it up. And so now it's negative of, let's see, don't need that. Negative of 1 over u. So and u is the cosine. Did I make a mistake? Seems too easy. One of these is minus, right? Plus, minus 1 is good. So I think that's right. And in general, if one of these numbers is odd, so the rule with these guys, if m or n is odd, change all but 1. Yeah, this doesn't even make any sense. Okay, I'll try it over here. Sorry. So, if m is odd, I'm going to use that to change m minus 1 to cosines. If n is odd, then I change n minus 1 to cosines to sines. Again, using sine squared plus cosine squared is 1. And if they're both even, this doesn't work. I'll describe in just a second. Okay? If they're both odd, pick your favorite. If you like sines, change to cosines. If you like sines, change to sines. Okay. So if they're both even, then you use a different identity to cut the power in half. So we use the fact that sine squared of x is 1/2 y minus cosine 2x, and then cosine squared of x is 1/2 y minus sine 2x. Still cosine, it's a plus. It just, I know it's right, I just didn't write it. So this cuts the power in half, and then now maybe one of the powers is odd and you use that trick. If not, do it again. If not, do it again. Eventually, you cut an even number in half enough, unless it's 0, you get down to an odd number. Okay?
Well, can I use the one that says sine 2 theta equals sine 2.
Well, you don't have a sine 2 theta, so it's not much use.
I mean, it says.
So it's not the angle that's even. I mean, the powers are even. So if I have an integral like, let's do the simplest one, like that, then the simplest case here is I would replace it with this, and now it becomes easy. Right? So this becomes, using this fact, 1/2 the integral of 1 minus the cosine of 2 theta d theta. And that's easy. This is just 1/2 theta minus sine 2 theta. But I'm letting u equal 2 theta, so du is 2d theta, so I pick up another half. So that became easy, because I changed the power from a 2 to a 1. If I had sine to the 4th, would have to do this trick twice. Right? A sine to the 4th would become stuffy in terms of this thing squared. Square it out, do it again. So these quickly get annoying, like if you have sine to the 16th, it takes a long time to get down to something normal. But you can keep cutting the powers in half until one becomes odd. So like if you had a sine to the 6th, you could do this trick, and now I have cosine cubes, and now I can use the other trick. Okay? People all right with this? So it's important to remember that the angle keeps doubling. Right? This is a cosine 2 theta, so that if I had to do it again, then it would become 4 theta, and so on. Okay, other questions? Yeah, you in the back.
Can we go over more about integrals?
Okay, they're all the same to me, but they're obviously not all the same to you, so sure. Do you have one in mind?
Yeah.
Okay?
The integral from 0 to infinity over x over e to the x.
X over
E to the x. E to the x. Yeah.
x over dx?
No, x over e to the x.
Oh, x over e to the x. Sure. Okay. So this one's okay at 0, because at 0 we have 0 over 1. It's just at infinity we have to deal with it. So this becomes limit, and just to rewrite it, that, but we still have to do the integral of x e to the minus x. In fact, it's probably easier to think of this way. It's the same, right? But it's easier to think of it this way because now what technique am I going to use to do this integral? Parts. I'm going to use parts, and I'm going to let this be my thing that I take the derivative of, and this be the thing I integrate. So by parts, I let u be x, so du is dx, and dv be e to the minus x dx, so v is minus e to the minus x. So then this integral becomes the integral of uv, the x is in front, evaluated from 0, that's an m, not an l, minus the integral of v du. So v is negative, so that becomes a plus, and we have that. This is again from 0 to m. Right? Okay? So now, this integral, this bit, this is the limit as m goes to infinity of minus m e to the minus m minus, at 0, well it's a minus, so it becomes a plus, 0. I guess it doesn't matter. So there's one limit we have to do. And then this integral is easy to do. The integral of e to the minus x, we already did it once. It's minus e to the minus x. So minus e to the minus m minus a minus 0, well, it's a 1. Okay so far? Okay. So now we just have to do these two limits. This limit's pretty easy. As m goes to infinity, 1 over e goes to 0. 1 over e to the n goes to 0, so this is 0. And so this piece goes to 0. This piece also goes to 0 because e grows faster than x. E to the x grows faster than x. So the limit of x over e to the x as x goes to infinity is 0. So I get 0 plus 0 plus 1. So it converges to 1. Unless I screwed up somewhere, which is not unheard of. Those of you in my lecture know that well. So in some sense, all of these are the same, but I can do more of them if you want. It seems everybody seems to have mastered integration by parts. So since nobody wants me to do integration by parts, because that's the one topic we haven't done anything about. We also haven't done anything on area between curves. Which one? Not parts. I meant partial fractions. So the two topics that we have not touched on are partial fractions and area between curves. Curves? Okay. Yeah. I've been trying to get people to ask me, but nobody's asked me. But he asked me for area between curves. Do you have one in mind? Okay. Do you want me to make one up? Do the one she wanted first? Okay. Do you have one in mind?
I just want to do a partial fraction of the denominator.
Okay. So I can either look for the book and hope that the book isn't mean, or I can just make one up and maybe the numbers will be equal. Because I'll make one up and maybe the numbers will be equal. Or do you want me to take it out of the book? I don't care.
Just
Make one up. Okay. How's that? So I suppose, actually you could try and do this one by trig substitution if you completely forgot integration by partial fractions, but partial fractions should be good here. So in fact, we're going to get two terms which involve stuff on top that isn't just a constant, right? Because I have an x squared and I have an x squared plus 1. I can't reduce this and I can't reduce that. Okay. So what I use is the fact, okay, I want it to look like something over x squared. So the thing that I want is when I split them up, I always want the power of the top to be 1 less than the power of the bottom, plus something else over x squared plus 1. So now that's what I need to solve. Okay? So if I cross multiply and I get, just on top, I get 3x equals, so ax plus, oh that was yep, oh well. So this one was messier than I had anticipated because I wasn't thinking. Cx plus d times x squared. So that's what I have to solve. So I guess I want to.
Wait, so let's say your denominator, the denominator had maybe x to the third and then it had so the top you're just putting it up be like ax to the third.
I need another letter. You have that.
Okay.
But let's not. Yeah.
Could you split, instead of doing x squared, can you just do x, like a over x plus b over x, and then cx plus d?
You can't do a over x plus b over x. You can do a over x plus b over x squared.
Okay.
And that's the same as this, except you get different numbers for A and B, but you get the same answer. So I prefer this because, see, there's nothing I can do with this. Well, okay, I could do x minus I, x plus I, but let's not go there. So I can't factor this anymore. So the rule of thumb that I prefer, I mean, the book says, okay, write this as A over x squared plus b over x plus cx plus d over x squared plus 1. It's the same. I'm just going to get a different number here. So here, actually. So I prefer to do it this way because it's the same. Okay, so let's just go ahead and do this. So now I can either multiply everything out and then equate coefficients, or I can pick various values of x. Either one. I like to use a mix, but if you prefer, I can go with just one. Which way do you prefer? Or just let me do whatever I do? Do whatever I'm going to do?
Wait, you're just taking the numbers.
Okay, so this has to be true for every value of x. That means that if I multiply everything out, so for example, I'm going to get an ax cubed term and a cx cubed term, that means a plus c has to be 0 if I multiply everything out. But I can also just pick numbers because it has to be true for every value of x. So for example, if x is 0, I get 0, 3 times x is 0, equals a times 0 plus b times 1, because x squared plus 1 is 1, plus 0, because x is 0. So just plugging in for x equals 0 kills everything and tells me immediately b is 0, I'm done with b. So b is 0. If x is, well, it's not obvious what else to pick here. Maybe 1's a good number. But if x is 1, I get 3 equals a plus b times 2 plus, well, b is 0, so that's gone. Plus, x is 1, so I get c plus d. So I know that a plus 2a plus c plus d is 3. If x is minus 1, then I get negative 3 equals negative a, b is 0, so that's done, times 2 plus d minus c times 1. And so now I have another equation here. Let me write those. Where should I write it? Here. So I already know b is 0, so I'm done with that. And I know that 2a plus c plus d equals 3, and negative 3 equals negative 2a plus negative c plus d. And if I add those two together, I get 0 equals 0 plus 0 plus 2d, so d is 0. So I don't need d either. Okay, so d is 0. So now I can go back again and see that since d is 0, I've got 3 equals 2a plus c, and negative 3 equals 2a minus c. So if I add those together, I get 4a. Is everything 0? What the heck? All right, I made a mistake somewhere. This is a negative. Yes, so this is no information to me. This is a negative, so this is no good for me. So I need to get another equation. So what other equation can I use here? Well, I notice here, if I multiply this out, that ax cubed plus cx cubed equals 0. So I know A plus C is 0. So A is negative C. So now I'm down to 1. Let's put, I'm sorry? So I'm just going to pick another number. How about 2? And I already know that A and C are opposite of each other. So I have picking x equals 2. This tells me that 6 equals A times 5. And B is 0, so that's gone. C is negative A, so that's negative A times 2 times 4. If I did this right, is that correct? Yeah. Okay. Let me write it a little longer. So I'm picking x equals 2. So 6, 3 times 2, equals A times 2. B is 0, so it's gone. Oh, it wasn't 5, it was 10. Yeah. Times 5. And then C here is negative A, so this is negative 2 times 4. Okay? Since D is 0. So that means 10A minus 8A is 6. So A is 3. And C is negative 3. And so after all of that garbage, we know that this equals 3 over x squared minus 3 over x squared plus 1. So my answer is, I didn't leave enough room. I'll write it here. So this 3 over x squared integrates to negative 3 over x. And this is 3 arctan. And as I said, you could have done a trig substitution and you should have gotten the same answer. But that was because it was an x squared. Okay? Now, I mean, this one, let me just let you know of the level of difficulty here. This one, if I put it on the test, I would expect maybe 10% of the students to be able to do it during the test. Maybe. I would expect probably 40%, 50% of the students to be able to start it, but only about 10% to be able to get all the way to the end on a test. What you can do on a test is much less than you can do on a homework. Because on a homework you can make mistakes and then you can relax and say, oh geez, I did a stupid thing, and then you fix it and so on. On a test it's a very different situation, and you make a lot more stupid mistakes. Yeah?
3x.
Probably. I mean, maybe I did it wrong. What should be 3x?
3x over 8.
No. Oh, A. Yes, A. You're right. Damn. See, I would be one of those students that didn't get full credit. So on this, if this were out of 10, I would probably get 7 or 8. So I know how hard the test is, and so I set the test so that, you know, about, how does the curve on the test work? It's not a curve based on how people do. So it's possible for everybody to get an F or everybody to get an A. I've never seen it happen. But in general, about 30% get a C, 30% get a B, 10% get an A. Maybe it's 15% A's, maybe it's 5% A's, depends on the class. And other people don't do so well. So Usually it's around 70%, maybe 80% that do better than awful. Yeah.
I'm not all that confident in my ability to recognize trig functions. If I wind up getting something weird, instead of something like R10 that's easily recognizable, how many points would you lose if we left it?
It kind of depends on how crucial that is to the problem. So like here, for this problem where I already screwed it up, if it's out of 10, then probably 2 or 3 of the points are being able to actually do the integrals. Now this integral was well, it's not that much harder. So this is a log, and that's, you make the substitution u equals x squared plus 1. So this one has no trig functions. So here, the integrals on this problem are probably like 20 to 30% of the points on the problem. Because the hard part on this problem is to be able to notice its partial fractions, set up the partial fractions correctly, solve the partial fractions, get the integrals, and now do the integrals. So, but if the problem is, what is this integral? And you say it's arc sine, you don't get a whole lot of points for that, right? So if it kind of depends on what the problem is testing. If the whole point of the problem is to recognize the inverse tangent as an integral, then you get 0 points for thinking that it's a log. If the whole point of the problem is to do, that's just a little piece of the problem, then it doesn't count for much. How much time? You have 90 minutes, an hour and a half. So, given that there's 9 problems, I don't know, you can divide better than me. But a couple of the problems are really easy. And so, I mean, another thing about the test, all of the problems are worth the same. In fact, they're all worth 20 points. So every problem is worth 20 points, so it's out of 180. Okay. Some of them are really easy. Some of them you should just look at them and almost write down the answer, maybe write one thing and then write down the answer. So that's 20 points for free. Some of them are quite involved and hard. So part of your job is to recognize what will take you a lot of time and what will take you not a lot of time. And do the problems that will take you not a lot of time first, so they're out of the way and done. They aren't necessarily the first problem or on the first page. So what you should do when you get the test is open it up and say, oh, that's easy, do that. That one looks hard, I'll skip it for now. That one's easy, da-da-da. So go through the test, do what you can do quickly, then go back through the test and do what takes you longer. You want to maximize the amount of, so what you don't want to do is find some hard problem, start with that, spend the whole 90 minutes doing that problem and only getting halfway, and then only getting 5 points out of 180 because you only got halfway through a problem that was hard and you didn't even get the free points. Well, they're not free. Okay? I don't even remember who asked that question. Nobody asked that question, I just said it. Yeah?
If I make such as square root -1,
Well, if you encountered the square root of -1, you did something a little bit weird, or you did something unexpected that works out to give you a square root of -1, and if you carry on, it will go away again. So, for example, I can factor this into x minus I, x plus I, if I really want to, and then I only have linear factors over here. But things will work out a little weirder, and I have to realize what to do with that. So none of the problems need to be done involving complex numbers. Yeah, go ahead. You have one that you think does. But there's no -1 here. I don't understand why you need to take a... Yeah? So this one is, so let me write the problem that he has. So this is on one of the practice exams. Oh, by the way, I will put the solutions to the practice exams up tomorrow. So all of the solutions will appear on the web page tomorrow. The reason they're not there now is to encourage you to try and do them before you see the answer. So again, remind me of the function. There has to be a t here somewhere. Wait a minute. Thank you. Okay, so h of t equals sine squared I t plus e to the square. Oh, I see what you're saying. Arctan 1 minus t squared minus t and g of t is the integral from 0 to g of x. And you're supposed to find so that's the question you're asking about. Well, this is use the fundamental theorem of calculus here. Right, you take the derivative, and then you're going to integrate it. Oh yeah, I guess it will have an I, won't it? It'll be e to the I. Because, so this is h of 1 minus h of minus 1. Yeah, so it'll have an I. Now it doesn't have an I. Yeah, okay, so now I understand your question. So that was just, I didn't know which problem that was, but the guy was just being silly. But yeah, so it's just this by the fundamental theorem of calculus. Okay. All right, so now I finally understand your question. I'm sorry it took me so long to realize. I can guarantee you that there should be no I's on the test that I wrote. I mean, your eyes should be on the test and not on your neighbor's test, but yeah. Other questions? Other things people want me to go over? Yeah. Sure. I'm listening. 1 to infinity. Wait. 1 to infinity of what squared? What's in, I'm sorry, 9 squared? Sine. Okay, it's just harder to hear you now. Sine squared x over x cubed. Is that it? Okay. So, and the question is not what is it, it is does it converge or not. Right? So the question is does this converge? So, what do we do? Yeah.
It's like 1 over x squared. Because it's bigger than that. So
Yeah, we compare it to 1 over x squared.
and if that's
Oh, this is a cube. Sorry. So we compare it to 1 over x cubed.
and if that converges, then that if it diverges, then that diverges.
Right.
Converges.
Well, no. It only goes one way.
Or no, it only works with
So we use the fact that sine squared of x is always less than 1. Because you're taking a number less than 1 and you're squaring it, you get something between 1 and 0. And so that means that if we divide it by x cubed, it's between 1 over x cubed and 0. And so if this converges, then happy times. If this doesn't converge, we know nothing. So now the question is, what about Does anyone know? I wrote it on the board a little while ago. Nobody knows? So let's check. So this is, so if you forget, we can just do it. So this is, if we integrate this guy, we get negative 2 over x squared from 1 to infinity. And if we take this is the limit as m goes to infinity of negative 2 over m squared minus a minus 2 over 1. As m goes to infinity, this goes to 0, so this is 2. And so the answer is yes, it converges. Hooray. Did I do something wrong? Should be a half? I don't know. Anyway, this converges, so yes. So this converges. This converges by comparison with the other guy. If this had diverged, we would get no information. So if we change this problem to sine squared over, square root x, we have to work a whole lot harder. Because we can't compare it to 1 over x squared. We have to compare it to something else. I don't want to do that. It's too hard. Yeah?
What if the x is the same problem, but x is divergence instead of convergence?
What
If instead x if it converges, or if x is divergent?
then you couldn't use this technique. That's what I just said. So if we change this problem, let's write a similar problem but not the same. So what do I want? I want something that diverges, so I want this to be bigger. So say we have that problem instead. So now this is always bigger than 1 over square root x. So square root x diverges. And since this is bigger, this diverges too. So you have to compare it to something else. Here, if I change this power to a square root, I can't directly compare it to 1 over square root x. I have to work harder. So instead I change the problem. You see? Okay. Okay. Other questions? You're all experts? You're all going to get A's? I wouldn't mind giving you all A's. If you're on, yeah.
Would you mind going over the area under 2 thirds?
Sure.
I know how to do that.
So these problems are pretty easy. Let me just, if we have two functions, f and g, then the area between them is just the integral of the top minus the bottom. So here g is on the top. And the only hard thing is to figure out where they cross. But that's an algebra problem. So you have to figure out what a and b are often. to know where they cross. So I can do a really stupid example where I can just do this, or maybe the other thing to point out is sometimes it's easier to integrate these things sideways. So if I have of course, I don't have an example in mind, but say I have some curve that looks like that, and I have another curve that looks like this, and I want to find this area. Let's make it look a little more obviously like this. Then I might want to integrate this way instead. I might want to integrate dy. So it's the same, I just have to take this minus this. So here is, say this is y equals f of x, and this has to be x equals g of y, because it's not a function. And so I would prefer probably to integrate this one this way, because to integrate this way, so I would do the integral from, I have to give these names, let's call this A, call this B. No, this one's the top. So this would be F inverse minus G. So I know this is not a specific example, and I can do a specific example, but that's the idea. It's easier to do this one dy. If you prefer to do it dx, so let me just draw the picture again. This is the part we're caring about. If we prefer to do it dx, we have to split this up and go from here, C, E, D, and then here the top curve is one branch of f inverse, and the other curve is the other branch of f inverse. So I have to do two different integrals. One over here, and one over here. Okay? So now let me, rather than just making one up, let me steal one from the book so that the numbers don't come out too horrendous, like 5 square root 17 over 18. I don't like any of those. Okay. How about 4x plus 4x plus y squared equals 12, x equals y. So, all right. So if we're doing this, we have to figure out what the region is, or we just have to figure out where they cross, and then figure out what to do here. So, what does the picture of this look like? Well, this is the same thing as saying y squared equals 12 minus 4x. This is a parabola opening this way, right? When x is 0, y is 0, y is 12. It goes through here 12, and then so I get something like this. Wait, no, I did this backwards, I'm sorry. I'm dumb. So this is the same, sorry. This way. Okay. So when x is 0, y is still 12. When y is 0, okay, then x is 3, and as y, why can't I do this? Is it open which way? 12 minus y squared should open down. That's right. It still does this. This is 3. Right? When x is 3, y is 0. Yes. Okay. Then y equals x. Right? I think that's right now, finally. And when do they cross? So I have to figure out when they cross. So that's just when y equals x equals 3 minus y squared over 4. So that is, the y values are y equals 3 minus y squared over 4, or 4y is 12 minus y squared. So y squared, y squared minus 4y minus 12 is 0. So that factors y minus 6 and y plus 2, right? Yes. So this crosses at -2. Oops, yeah, and 6. So my picture is a little bit off, but okay. And now the area is pretty easy now. We're going to integrate dy. And if we integrate dy, we integrate from -2 to 6 of wherever the function went. The top curve, which is the parabola, 3 minus y squared over 4 minus the bottom curve, dx. I'm sorry? Yeah, that's a y. All right, so this is the top, or actually the right, and this is the left. And so now we just get 3y minus y cubed over 12 minus y squared over 2 from -2 to 6, which is 18 minus whatever 6 cubed is, 36 over 2 minus we get when we plug in -2, so -6 minus plus 8 over 12 minus 4 over 2. So this is 36 over 2, 72 over 2. 8 over 12 is 2 over 3. Except this is a minus. It's some number. This is minus 18 plus 6 is minus 12 minus 10. So I get that, but maybe I screwed up. Okay? So, I mean, these are all this kind of thing. Yeah?
In one of the older problems, there was a multiple choice answer.
Yeah, so one of the homework problems was broken, and there was a multiple choice answer with one choice. Well, 3 points for you. So So the problem is now labeled, if you go back and do it, the problem is now labeled as defective. I didn't take it away because some people had done it and I didn't want to take away the points. It's still a good problem, it's just the last part is stupid now because it says, if the answer is 5, what's the answer? Other questions? Issues?
So no more early points?
If they fix the early point issue, then I'll go back to it. The problem is that the mechanism where early points were detected worked for some people and gave some people early points all the time. And a few people got jealous when their neighbors got early points for doing it 2 minutes before it was due. So, okay, so there's another review session on Tuesday. If you think of other things to ask between now and Tuesday, then plan. The other review session on Tuesday is shorter. It's only 1 hour and 20 minutes because they have to get out of the room. Yeah.
When did that one end?
That one is 6:50. It's in the time slot before your exam. So what that slot is, what, 6:50 to 8:10? So the review is 6:50 to 8:10. It's in Old Engineering 143. There's a physics exam afterwards. I mean, you seem to have run out of questions this afternoon. So maybe you're all prepared. Or maybe you haven't even thought about it yet. I don't know. There's also, I mean, I don't know, you probably received an email about a discussion board. There have been 2 questions asked. I answered them both. But there's something called Piazza. You might have deleted it because it looked like spam. But I set up a discussion board so that you can post questions there. And your other students can answer them or the instructors can answer them. So, okay. See you, well, I'll see a few of you tomorrow, and the other ones I won't even see you on Thursday. So I'll see you someday.